Today I'm going to talk about CKM matrix. So here is the CKM matrix, which actually talk about the mixing of quarks. So what is the motivation? I mean, how this matrix came into being? What was the requirement? Actually the first requirement was that there was a mixing. If we look at the charged current term of the electroweak Lagrangian, then we can see a coupling between the up quark and the down quark. So basically it's not true that the up quark only couples with the down quark. It can also, in general, it can couple with the strange quark and also with the bottom quark. But I mean, the strongest coupling is with the down quark, and then the less stronger is with the strange quark, and the weakest coupling between is the up and the bottom quark. Anyway, we get mixing of the quarks, and that's why we need CKM matrix. So let's jump into that and go into the details. Okay, so CKM matrix is basically if we look at this, there are actually 9 parameters, and ng here G represents the generation. So there are actually 3 generations in the standard model of quarks, and also for the leptons. And another thing is that according to standard model theory, the minimum requirement for the generation is 3, and there is no upper limit for the maximum requirement for the number of generations. And why the minimum requirement is 3 generations is because of the fact that if we don't have 3 generations, we cannot accommodate the CPU violation in the standard model. Anyway, we have 3 generations, and in CKM matrix we have 9 variables, and if we look at that, then we can have 3 into 3 9 plus 3 12. We can have 12 angles and moduli, and then we can have 3 into 3 9 minus 3. We can have 6 complex phases. But the standard model theory tells us that the CKM matrix is indeed the unitary matrix. So using this unitarity condition, we can reduce a number of parameters. So by reduction of some parameters, and by using the unitarity condition, we can get ng into ng minus 1 upon 2 moduli. That will be the 3 Euler angles for number of generation equal to 3, and we will have one complex phase for 3 generations. So here's the expression for the complex for the number of phases. So first of all, let's look at the start of look at the first ever work on quark mixing. The first ever work on the quark mixing was done by Cabbibo, who was an Italian physicist. He actually described the quark mixing mechanism for the 2 families of the quarks, and this right here is Cabbibo matrix, and theta of C is actually Cabbibo angle, which is very small, but anyway, that can give us the mixing of quarks in 2 families. D prime here is the mass eigenstate quark, and D is the weak eigenstate. So normally we write doublet like this, U and D bar. So D bar is actually the mass eigenstate, and we can use U bar and D. It purely depends on the convention that you are using. So this is Cabbibo matrix, and if we look for the three generations, then we have CKM matrix, Cabbibo, Kobayashi and Masakawa, the three physicists whose CKM matrix is named after their names: CKM, Cabbibo, Kobayashi and Masakawa. Okay, so in the first row we have the coupling of up quark with the three down type quarks, which are down, strange and bottom. In the second row we have charms coupling with all three down type quarks, and at last we have the tops coupling with all three down type quarks. Anyway, this is the standard representation, and in Wolfstein representation he used the parameters lambda, a and rho and eta, and this is the Wolfenstein representation, and this is actually an approximation. So we can also have in general the lambdas in the lambda to the fourth power or the fourth order. So that are actually too small, so we can neglect that. Lambda here is actually sine of theta c, which is Cabbibo's angle, which is equal to 0.223. A is equal to 0.83, and rho square plus eta square in the square root is equal to 0.48. And if in Wolfenstein representation, if eta is not equal to 0, then this will lead to the CP violation. And in order to have a CP violation, we must have at least one complex phase. And if we look at this standard representation, I have written here C12 and S12, C13, S23, C23 represents the cosine of 12, cosine of 23, or cosine of 13, sine of 12. So I can also write this, sorry. Cosine of ij theta is actually Cij, and sine of ij theta is actually Sij. So in general, if we multiply all these three matrices together, so we get a combined matrix, which is also valid. Now we have to, now that we have introduced this matrix, after all, we have to measure the elements or the parameters of the matrix, and by using the unitarity condition we have already reduced reduced the parameters. So now let's see how we can measure the parameters of this CKM matrix. So first of all, in order to validate the standard model theory, for instance, we can see the Yukawa coupling. When we do the Yukawa coupling, we needed to introduce the CKM matrix in the charged current Lagrangian term of the electroweak Lagrangian. So to verify the standard model theory, we need to verify that if the CKM matrix exists, and if it exists, it should be unitary, because that is the only thing which the theory tells us. Now, the fact that we are dealing with the quarks, and quarks are not found in nature as free particles due to the phenomenon, the confinement. So we don't find them as free particles, we find them in hadrons. So it is very difficult to measure these parameters. For the moment, let's look for the coupling for VUD, VUS, I mean for the two families, and let's look through the semi-leptonic decay and see where things are going. So a down quark, in this Feynman diagram, a down quark is decaying into an up quark via W boson, and then W boson decays into an electron and electron neutrino. Okay, so we can measure these parameters. Actually, if we look at this vertex is actually Vij. So Ij corresponds to the up, down, and strange. I mean the three quarks. It corresponds to the quarks generation. So we can look into the super allowed nucleate beta decays, which are pure vector transition states, or we can look into three body decays. Three body decay processes, also semi-leptonic decay. Let's say a pion decay into a neutral pion and a positron and anti-electron neutrino, or let's say the decay of charged cation into a positron or a electron along with the neutral pion and neutrino, corresponding neutrino. Okay, so the measurement result for the up, down, and CS, I mean up and down belong to the same doublet, and CS also, the charm and strange also belong to the same doublet, so their coupling is the strongest one, so that's why they are about 1. I will show you the explicit calculations later. And the coupling of the first generation with the second generation, for instance the US and the CD, it is around 0.2. And if we look about the coupling of the first generation and the third generation, is about let's say the first generation and the third generation, the coupling of U and B is about 10 to the minus 3, and the coupling of charm and B, the second generation and the third generation, is about 10 to the minus 2 respectively. Now we talked about the first two families of the quarks, the top the up quark, down quark, strange quark, even the B quark, the bottom or the beauty quark, but we have not discussed about the top quark. Okay, so the fact that top quark is so heavy that we cannot actually measure, it is so heavy that it has no time to hadronize. I mean it has mass, it is actually the heaviest particle in the whole standard model, having mass of 174 JeV. So we know that the decay width is proportional to 1/m. So its lifetime is, I mean not at all, its lifetime is nothing, it's very small. So we say that it does not have any time to hadronize. So if it does not hadronize, so how we are going to have any idea about the top quark? So for the top quark we can look into the B0 and B0 bar meson oscillations, and I have made another separate video for that, in which I showed that the difference in the mass of B0 and B0 bar is proportional to VTD and VTD TB. So from that we can have an idea about the coupling of top with the other generations of quarks. Anyway, so that is one option to know about the top quark, and the other option is the direct decay of quark into a B quark and a W boson. And in this case, this W boson is actually a real boson which is decaying. So anyway, but you know, this process is very rare, and if it is very rare, we have very low statistics. So it is very hard indeed, even in this case. I mean, the decay of the decay of top quark into a B and W plus. And if you look at the tevatron, I mean, the first time the top quark was discovered in tevatron, and top quarks are also produced in LHC, but at LHC and in tevatron we produce the TT bar pair. Anyway, but the tops coupling, I mean the VTB or VTS or VTD has also been discovered, and the unitarity condition for the CKM matrix has been proved. Okay, now we are going to look at these semi-leptonic decays explicitly. For instance, and now, well, actually, why we are looking at these processes, at these three-body decays, because we are interested in Vij, I mean the parameters of the CKM matrix. Now if you look at this vortex is actually VUD. Yeah, so here a pion is decaying into neutral pion, and positron and electron neutrino. I think, yeah, it's electron neutrino. And in this process, in this Feynman diagram, the U quark is a spectator, and if we have a hadronic decay, I mean if we have a baryon, then we will have two quarks as spectators. Okay, now this specific process, this has a branching ratio of 10 to the minus 8, which is very small, means very small branching ratio. So in order to get I mean in order to have a statistical fluctuation of 10 to the minus 3, I mean in order to have a small error, we need 10 to the 14 pions. And another problem is that the Q value of this process is also low, because of the fact that the mass difference of the two pions is very small. Okay, so if you look at the magnitude of this process, then it is proportional to F plus of Q square GF U VUD P mu nu E gamma mu 1 minus gamma 5 E, where F plus Q square is actually the form factor, P mu is the sum of momenta of the interacting particles, VUD is the vortex that the VUD is the actually the parameter that we are interested in, and here nu is nu E, I mean left-handed neutrino is interacting with an electron. Anyway, this is the expression, and if we look into the width of this decay, This is proportional to the branching ratio of this tree body decay divided by the lifetime of the pipe, and this is proportional to gf square, the Fermi constant square, VUD square, d5. D is actually the difference of the masses of pion, the fact that pion's mass is so low, so we use here the difference of their masses. And we can also see in the last there is delta em is the corrections, electromagnetic corrections in these kind of process. And electromagnetic corrections are very important, as if we see into the Z line shape. So if we don't include the electromagnetic corrections, then we will have a totally different result that will not be comparable with the theoretical results. So actually, cut the long story short, in Z line shape the electromagnetic corrections are around 30%, and it's very important. So from these calculations, I mean, if we do these calculations, we find that the VUD is around 1, actual value is 0.97 something. You can see it on the Wikipedia or somewhere else. And this experiment has been done in Zurich, and the name of the experiment is pi beta. And in that experiment, actually they measured the two emitted pions, and for that they used, I think, cesium iodide scintillator to detect that. Anyway, pi beta was the experiment in Zurich where they measured this VUD parameter. And VUD is proportional to the cosine of theta c, which is the Cabbibo angle. And one thing that I want to tell you, that the processes, I mean the parameter VUS and VCD or VCB, these processes are proportional to the sine theta of C, and sine theta of C are actually Cabbibo suppressed processes. And later I will show you that I will show you the Cabbibo suppressed processes. Anyway, here is another semi-leptonic decay of the cation into a pi plus electron and electron neutrino, or pi minus positron into electron neutrino, or electron antineutrino. Look at this process. This vortex right here is actually VUS and this is proportional to sine of theta c, and decay width for this process is given right here. Here we also include the delta EW, the electroweak corrections, and also the electromagnetic corrections. The electromagnetic corrections in this process is about 0.5%, and electroweak corrections are around 5%. And I plus parameter here accounts for integration over the running of momenta, and this parameter is proportional to sine of theta c, and this is Cabbibo suppressed. Actually also VUS, as I showed you earlier, is around 0.2 something. Maybe I'll show you the exact value, or you can see it on Google or somewhere else. Okay, so here we can also I mean, we don't have to look into all these difficult processes. There is a simple procedure, rough calculations by which we can calculate the coupling, and these coupling are proportional. For example, the coupling between the same generation particles like BUD, BCS or BT is proportional to cosine of theta. I'm sorry, it's not W, it's theta C. Theta C, the Cabbibo angle. The fact that Cabbibo angle is very small, it's around 0, I mean very small, so cosine of theta C is around 1, not exactly 1 but around 1. So the coupling of VUD into the same generation is around 1, and coupling across the generation like the VUS or VCD is around proportional to sinus of theta C. Okay, and the fact that theta C is very theta of C is very small, so sinus of theta C is proportional to 0, not exactly 0, but it can take any other values. Now I am going to show you some processes in which we are going to see we are going to estimate a naive estimate about the couplings among the same generation or the different generations using the Cabbibo angle. Okay, there are some processes. The decay rates for these processes in which D meson decays into cation and a pion, and similarly there are other processes. And now if we look at this process, which is actually let me take this process. This process is purely hadronic process, and if we look at the vortices, this vortex is proportional to CD, and this vortex is proportional to US. So we can say that the decay of this process is proportional to VCD square and VUS square. VCD is proportional to sine of theta C, and VUS is also proportional to sine of theta C. So let's jump to the conclusion. So we can look at the different ratios for these various processes. For instance, let's look at the ratio of decay of D meson into two cions, the two charged cions, and the decay of D0 meson into cation and a pion. And this the first process is proportional to VCS square and VUS square, which is actually the proportional to the sine of theta C. Theta C is the Cabbibo angle. And in the other process, this is proportional to VCS and VUD. So we can cancel out the VCS with the VCS, and eventually we get VUS and VUD. VUS is proportional to sine square of theta C, because it is across the generation. It is the coupling between the first generation and the second generation. And in the denominator we see that we have VUD, which is the coupling among the between the first generation, I mean the up and the down quark, and the coupling within the same generation is proportional to cosine of theta C. So in that way we can say that this is proportional to tangent square of theta C, and if we put in the value of Cabbibo angle, we can estimate the ratio to be 0.05. So we can try all the different combinations and get an naive estimation about the coupling between different generations. Okay.